Good morning everyone, my name is Pranay. I am from CSE AML section C. Today my topic of physics is characterization of photoionic crystals. Introduction to photonic crystals. Photonic crystals are periodically structured materials that affect the propagation of electromagnetic waves through them due to their repetition variation in refractive index. This periodically leads to constructive and destructive interference, resulting in the formation of photonic band gaps, frequently range in materials that cannot propagate through material. Principle of operation: the periodically dielectrical structure scatters light at regular intervals. Bragg diffraction causes certain wavelength to interfere destructively. This prevents light of those wavelengths from propagating in certain direction, forming photoionic bands. Structural types: photonic bands. Photonic crystals are characterized based on their dimensionally of periodicity. 1D photonic crystals, variation in one direction. 2D photonic crystal, periodicity in two dimensions. 3D photonic crystals, full 3D periodical structures. Photonic band gap, frequency range where electromagnetic waves are prohibited from propagating. High control over light enables manipulation of light paths, localization and confinement at the nanoscale. Anisotropy, directional dependence of light propagation due to structure geometry. Application of photonic crystals, optical communication, LED lasers, sensors. Why characterization important in photonic crystals? Characterization plays a crucial role in development application of photonic crystal structures. While the theoretical design of PHC is often performed using computational models such as finite difference time domain or plane wave expansion, and real world fabrication can include deviations to limitations in lithography, etching and material deposition process. Therefore, it becomes essential to assess where the fabricated photonic crystal matches the intended design both structurally and functionally. This is where characterization becomes indispensable. One of the most immediate purposes of characterization is structural validation. Photonic crystals rely on a periodic arrangement of dielectric materials with a precise control over lattice, constant, hole or rod dimensions and sympathy error. Deviations in these parameters can significant the optical response. Such techniques as SE and AFM are typically employed to inspect the geometry and the surface quality of fabricated structures. Structural characterization confirms whether the periodicity and the design tolerances have been maintained and helps in the identity of fabrication defects such as roughness, misalignments or complete etching. Beyond structural features, the optical properties of photonic crystals must be characterized to their ability manipulate light. The most proper feature of PHC is the photonic band, a range of wavelengths that are forbidden from propagating through the material. Characterization techniques such as Fourier transform, infrared spectroscopy (FT), and transmission and reflection spectroscopy and angle resolved measurements are used to study how light interacts with the crystal. These tests help the verify of presence, location and the width of photonic band gaps. Whether the device behaves as theoretically predicted. Characterization is equal to academic research and industrial purposes research. It also provides critical feedback for understanding novel photonic behaviors and improving design methodologies in industries. It serves as a quality control tool to ensure batch to batch consistency, reliability in large scale consistency and reliability. Without vigorous characterization, it would be nearly impossible to commercialize PHC based technologies as real world applications demand predictability, durability, reproducibility. Types of crystals. Photonic crystals are divided into 1D, 2D, 3D crystals. Not only defines how light interacts with the structure but also influences the complexity of fabrication and the range of practical applications. Understanding the types crucial help for appropriate structure for a specific optical function such as waveguiding, filtering, enhancing light emission. 1D photonic crystals. 1D photonic crystals have a periodic variation of refractive index in one direction. Simplest example is Bragg mirror. These layers cause constructive and destructive interference for specific wavelengths of light, leading to a photonic band gap in the reflection spectrum. Due to their simplicity and ease of fabrication, 2D photonic crystals have periodicity in two directions while being uniform in the third. Common designs include air holes etched into a dielectric slab or dielectric rods arranged in a 2D lattice. These structures are widely used in integrated photonics because they allow for control of light for propagation in planar devices. A key advantage of 2D PHCs is their ability to guide and localize light in very small regions, which is essential for creating compact photonic circuits. Applications include waveguides, beam splitters, resonators, biosensors. Their fabrication is more complex than 1D structures, typically requiring advanced lithography and etching techniques. 3D photonic crystals. 3D photonic crystals have periodic variation in three spatial dimensions, giving them the most complete control over the propagation of light. Next, Fabrication techniques for photonic crystals. The functionality of photonic crystals relies on heavily on the precision of their structural geometry, especially the periodic variation of refractive index at the micro or nanoscale. Therefore, the fabrication is a critical step in the bringing theoretical designs into practical devices. The choice of fabrication method depends upon the types of PHC, the material system, and the desired operating wavelength. A wide range of fabrication techniques has been developed, ranging from traditional semiconductor processing to advanced self-assembly and directing laser warning. Photolithography. Photolithography is one of the common method used for fabricating 1D 2D photonic crystals on a substrate. In this method, a photosensitive material is patterned using UV light through a mask. The pattern is entered, then transferred to the underlying material using etching techniques. Electron beam lithography. For a high precision, EBL is used to define features with nanometer scale accuracy, making it a deal for 2D photonic crystals. This technique includes a focus electron beam to write patterns directly onto an electron sensitive resist. Although EBL provides an excellent resolution, it is a slow and expensive process best suited for prototyping or research rather than large scale manufacturing. Etching techniques react to RIE. RIE is a plasma based etching method that offers anisotropic etching, inductively coupled plasma ICP etching. ICP etching offers high rate etching technique rather than radio control conventional RIE. Next, self-assembly techniques: colloidal self-assembly, block polymer self-assembly, direct laser writing, nano imprint lithography. Characterization techniques for photonic crystals. Characterization techniques for photonic crystals. After the fabrication of photonic crystals, it is crucial to verify whether the structure meets the intended design specifications and exhibits the desired optical properties. This is achieved through a variety of characterization techniques, which can be broadly divided into structural characterization and optical characterization. These methods provide critical feedback to the fabrication process and the functional design of photonic devices. SEM is one of the most used techniques visualizing photonic at a high resolution. It improves detailed images of the surface morphology and periodic patterns at the non-scale. SEM is especially used for evaluating geometry, periodicity, and defects in 1D, 2D photonic crystals such as diameter of air holes or spacing between rods. Cross-sectional SEM can also be used to analyze many structures. Next, AFM, transmission electron microscopy. TEM is used for high resolution. After using for high resolution optical characterization techniques, FTIR is to measure transmission and reflection intra, and it is used to help in identifying photonic band gaps. UV VSNIR spectroscopy, it is used to operating near or far infrared images. Next, angle result spectroscopy. Angle result spectroscopy explains that angular dependence of photo band gap, and it exhibits anisotropic behavior, directionality of light propagation. Band structure and module mapping. Band structure module mapping is often combination of FT, DT, and experimental data, and NSOM is optical modes plus localization of light. Photonic band gap concept, importance, and measurements. Photonic PBG is one of the fundamental and defining feature of photonic crystal. Just an electron band in semiconductor prevents electrons of certain energy from propagating. Next, photonic band refers to a range of frequencies. It occurs due to multiple scattering and interference of electromagnetic waves in the periodic medium, which disrupts certain modes of propagation. Photonic bonds enable a precise control of light, confine light in cavities or detects, guide lights in wavegates, filter specific wavelengths, enhance or suppress spontaneous emission. It is also used and valuable in quantum optics. Defects occurs in photonic crystals, point defects, line crystals, and surface defects. And applications are microcavities, waveguides, resonators, and yeah. Defects are localized modes, and wave guiding. Wave guiding can also be light is confined with the defect and cannot leak into surrounding PBG material. And resonant cavities. Resonant cavities are point defect create resonant cavities from high Q to, it is important, Q factor and Q whole module cavity. Simulation techniques essential to predict and optimize PHC behavior. Advantage of photonic crystals: precise control over light propagation, customizable optical through structure. Next, challenges is fabrication difficulty, material limitations, band gap may be directional, sensitivity to detects, and limited scalability. In conclusion, we have discussed that the photonic crystals have emerged as transformative class of materials in modern optics and photonics. But the successful implementation is due to not only an innovative design but also precise and scalable fabrication. Next, characterization. The characterization, it played a pivotal role bridging the gap between design and functionality. Without accuracy and structural optical characterization, it would be impossible to validate structures. Techniques such as AFM, FTIR, SCM helped a lot throughout the development cycle. The characterization of photonic crystals ensures the reliability and reproducibility of their products. Next, while the potential of photonic crystals is vast, severe challenges remain. Fabricating three-dimensional structures with complete photonic bond is still difficult and resource intensive. Achieving high refractive index, contrast, and minimizing structural disorder are ongoing concerns. Furthermore, integration with existing In conclusion, the photonic crystals are not just a topic of academic interest but a foundational technology of photonics revolution. Their fabrication and characterization are crucial steps in realizing their full potential. As we continue to refine our ability to control light at the nanoscale, photonic crystals will be heart of devices that are faster, smaller, and more efficient and more versatile than ever before. And thank you everyone for my presentation, and thank you everyone for listening my presentation. And I conclude my presentation, the characterization of photonic crystals. Thank you.